Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're gonna talk about acid mine drainage. So let's dive deep into it. So what exactly we are talking about here? Well, we are talking about acid mine drainage or AMD, and you will hear this word way too often. Yeah, I know it's similar to the computer PC part, but if you ever read any environmental study, generally this term will keep coming up. Acid mine drainage, and it is brutal. Why it is so brutal? Well, it's an outflow of acidic water on surface or underground, which basically is naughty HO2, which comes from, this is the problematic part, it comes from metal mines. Now you may say, hey, those are not that common. Also comes from coal mine, which is ludicrously common. So that means fundamentally wherever, which continent or country you are occupying, you have this problem. It's a brutal problem, and it's a headache. It's a big of headache, and it contaminates water. Basically, that's what it has to deal with primarily. It contaminates water on a large scale. That's the problematic aspect. You may be like, hey, I have a small mine, how big it effect could be? Yeah, it could wipe out a whole river, and we have learned it the hard way. So it's a very serious large scale problem. On top of that, it can take care of the top parts, as in like anything that is surface level, and also underground, meaning you could literally have a scenario where people could not drill into the ground and pull out water simply because that water is not water, it's acid. So fundamentally, it's a brutal problem, and AMD has to be dealt with and managed properly because it happens from, well, almost every mine, and we have to be very mindful with it. So how the heck these puppies are formed? Well, you have to understand sulfide minerals are existing in almost all mines, and whenever you have coals and all that, generally there is a good chance it's surrounded by these things. So it's almost same like how you have coal and there is a good chance there would be gas pocket. It's same thing. Perite, basically fool's gold. It's a mineral that's found way too often, way too, well, everywhere basically, and it gets love from H2O and air, basically water and oxygen. It gets love. What does that happen? It's a mineral. It oxidizes, quote unquote, it rusts, and then it becomes sulfuric acid. Now, so far, that's bad. Then it gets worse. That sulfuric acid now makes the basically water pH level drop. It drops to 2 or 3, and be mindful, 2 is brutally low. And at that point in time, not only you have sulfuric acid, you have a water that is acting like a solid acid. At that point, it does what we call second stage, which is heavy metal leaching, meaning it will go through things, cracks, fissures, other minerals, other stuff, and it will leach heavy metals out of it. And at that point in time, this is bad. So not only you have acidic water, you have heavy metal laced water. So oxidation of perlite, that creates oxidation of ferrous irons, as in like Fe reacts, then formation of sulfuric acid. Now this is the how chemistry expert will tell you, because it's a complicated thing. In simplest term, think in this way. FeS2 gets naughty with O2 and with H2O, and then the outcome is FeSO4, ferrous sulfate, and then you have H2SO4, the death, sulfuric acid basically. And you can see that this is the mine data from all the sources, and they found out like the pH levels are like bad. It's like if you are lucky, you have pH level of 7, which is not that bad, but then it can drop to 2.5, and some scenarios 3.5 is quite obvious, like many mines are 3.5. So yeah, that's bad. So pH change alone is harmful. On top of that, it terminates basically microbial life, fish life, tree life, or human. Basically, it will not let you live. If this is happening, bad things, run. And why it's such a big deal? Well, nature has this sort of processes happening all the time. That's not an issue. Issue is that when human does human intervention, we amplify it. Basically, instead of having 10 liters of it, what if we have 10 trillion liters of it? What if instead of having a minor water crack, what if we had a rivers flowing through it? That's the issue. We just amplified the vectors that was not meant to be amplified, not to this extent. That's the issue. We are unbalancing it. So formation is basically you have FeS2 reacting and giving us H2SO4. It's bad. So what are the consequences? Well, consequences should be understood with this. Basically, water is, well, universal solvent, and we are used to it. And clean and normal water is basically clean rain should give you around 5.6. Healthy lake should be 6.5. And then, pure water, distilled water, that's why distilled water is not good for us. It's 7. Salty water, seawater goes to pH 8. So there is a very good amount of health can be had in this median zone, neutral zone. You will gonna have a lot of healthy things in neutral zone. Yeah, it has to go up, as in like acid rain starts to happen at 4, and basically let that be very clear. If you have acid, raw acid, as in like pH level 4, you have this liquid bath that is 4, no fish can survive in it, flat out. Like, hope that it dilutes, hope it drops below that pH level. But if you have let's say a dry bed and you had acid rain happening on it, that lake will not create a scenario where you can put fish in there, even though it could be a rainwater system, but it will be too acidic. So all fishes die at 4.2, and that's why that creek, if it touches rivers, it will poof anything nearby. And then you have pH level 3, which is orange juice. It's reaching a point where even biological life is like, that is pH 3, and then you have pH 2, which is vinegar and all that jazz. Brutal. That's brutal territory. pH 0 is raw battery acid, meaning if it falls on your skin, it will hurt badly. So far, that just tells us a problem. Now, here's the horrifying part of it. It can last for centuries. Now, first question in your mind would be, how do we know it will actually last for that long? Well, we have been dealing with this. You have to understand the modern world dynamic is a bit different than what it used to be compared to earlier industrial revolution. In those times, everybody was local, meaning I found this quarry where I'm mining something useful. I'm finding this coal mine, I'm mining coal out of it. Everything was very local. So that was a very early era, as in like late 1800s, 1850s, things of that nature. World started to grow. Those architecture no longer could survive it. Then people moved out, things happened. And here's the deal, those mines that were shut down or abandoned, they are still leaching. Yes, after 100 years. After more than 100 years, they are still leaching. And yes, still bad, still painful, still toxic. So fundamentally speaking, we have learned this the hard way, that this can last for centuries, because we are dealing with it and they have no basically a mark of like it's ever gonna slow down, because again we exposed way too much. Nature is like, okay, in millions years of course it's gonna fade away, but it's the same thing with like a radioactive waste. It's like, yeah, millions or billions of years of course it will fade away, but it's not there yet. We will not be there for that long. We have to make sure that it's sorted quickly. So mine has shut down or abandoned, both of them cause an issue, because you have to because we have learned the hard way. Modern times, as in like the 1950s plus, almost all countries that had wisdom introduced strict laws that they understood it very well. Like for quick profit, poofing a whole river is not acceptable. So all these mines, they took a little bit of their profit, handled it. Now here's the deal. What happens after the mine shutdowns? Whose job it is? No one's. That's the scary part. That's why abandoned mine or shut down mines are horrible. And eventually it will end any natural balance, because you have to understand, you are putting acid, raw acid, into a river stream. What will happen? First, it will poof small animals that are sensitive to it. Okay, what happens? Now you have basically the bottom rung of the food ladder. Bottom ladder cripples the upper one cripples even the upper one. Poof, gone. So fundamentally, it will end. It's called a like death river. Like if it happens here, it will slowly over time remove whatever have you, like trees, microbial life. Certain microbial life will survive, but majority will be poofed, and any natural semblance of balance would be destroyed. If this is happening, you're dead. So fundamentally, it's very brutal, and it makes water unsuitable for basically low-cost drinking water solutions. Can we sort water from basically things that we need to? Like if we need water from seawater, can we get it? Absolutely, we have the technology. Then why don't we? It's expensive. It's always the same thing. It's too goddamn expensive. So what about this? This will make seawater desalination look free. That's how expensive it is. And be mindful, this is fresh water. We are contaminating fresh water sources. So it is brutal. And we are still trying to get in the grips of it, how much damage it causes, because what I'm focusing on is the bulk order of it, but there are also a smaller order of it which is causing even more harmful. Like we have old mines that were like built, abandoned, forgotten, then people randomly figured out, hey, why the heck our groundwater is now acid? And then it's like, yeah, there was this mine that was abandoned in like 70s, and now it's like, yeah, we are dying because of it. So it's a very consequential scenario. We have to learn it, we have to understand it, and it's not something that you can ignore. Let that be very clear. Ignoring it is not an option. Poverty cannot justify ignoring this, and countries are learning it the hard way. So what is the mitigation strategy? Thankfully, we have done this for centuries, so we did understand that we gotta sort it out. So nature does have a natural tool to sort of manage it, that is CaO, lime basically. So it's a large scale tool that allows to filter this puppy out. So what does happen? You introduce lime, it basically increases the pH. So instead of going from super acidic to it goes to mildly acidic or neutral, and that makes a scenario where metal that was leached out of it from the mineral bed, it's no longer stable there. It's like I'm not dissolved. It's the same thing, how temperature directly affects how much gases can be trapped into the water. Same thing happens with pH level. You change the pH level, it affects how much things can be in there. So you change the pH, now that metals are becoming insoluble, they are like starting to precipitate, it's going to go down. At that point in time, you're going to boost that puppy. You're going to boost that puppy with aeration. You're going to pump some air into it. Or if it's a pond structure, you're going to have a structure where water is falling like this, lot of small ladders that will allow a lot of air mixing. So what does that do? That does raw oxygenation. So that oxygenation basically rusts iron and manganese, which helps you into the precipitation. It allows all those metals to leach out very effectively. And mix of these two tools, basically aeration and lime, so far is the best large scale method that we have. Because here's the deal, can you do other this or that? Absolutely, there is a whole list of it. That's why we have chemistry books. That's not an issue is, do we have any tool that I can say this mine is in a very heavily rained area, can we sort it out? Only this technology will survive. And this is the only thing I'm seeing largely deployed. There are other systems also, that be very clear. People have been experimenting with it, but this is one of those things that I can say, and you have enough history and experience where it's like, nah, yeah, it works, and it's a large enough scale that justifies it. So mixing these two, what does that mean? That simply means, let's say you are in a drier kind of state, and you have basically because generally you are digging deep, there is a very good chance you have a water reservoir that is draining into it. You're going to pump it out, okay, but it's not a lot of water, and you do not have too much rain, so it's not going to be bonkers amount of water. So people can do this. Basically, they're going to make a wandering path. That path will be covered with limestone, and that lime will sort it out. Basically, lime will reduce the pH, and then the iron and all that will oxidize, and because it's rocky, it has so much aeration site, then iron is basically create a formation layer of it. Now this is awesome. It's a very low cost solution. It does work great, but it has two serious limitations. First, it requires you to keep replacing those rocks. Basically, you have to keep, because here's the deal, once it's covered by iron, it's no longer active anymore. It's like you isolated it. So it's a very good for low flow scenarios, but not a really good solution for long term, especially for some places that has a big ass mine which has huge ass rainfall on it. Yeah, this is like, bro, I will be overwhelmed very quickly. So mix of these tools are used. Some scenarios they have ponds, and in the ponds they could have clever tricks. For example, they would have a limestones that is reducing the pH, but they will also put something that reduces oxygen there. Right? Why would you want to reduce it? Wouldn't it help it? Well, here's the deal. You can act those things in stages, meaning you are reducing the pH, and if you have oxygen, it will turbocharge the basically precipitation rate. But what if you do not have oxygen? Some will still precipitate, but majority won't. But if you have high enough flow rate and things are just right, you can literally have a pond bed. Basically, pond A, water comes in, pH level goes down, as in goes up. Basically, it goes from acid to base, and acid to neutral, and you just move it to second pond. Now you dump bonkers amount of oxygen, and benefit of that is your limestone does not run out as quickly, meaning it does not become isolated, covered in gunk. Yeah, that's the best way of putting it. You basically delay how long it takes to gunk up the limestone, and you can get more oomph out of every truck of limestone that you have shipped. So that's a clever usage of it. So you can have pond based structure where one pond, even though it should have sedimentation, it will not let it. Like you can put charcoal and things of that nature which removes oxygen from water, or you make sure the water is not very disturbed. It's very little aeration when it reaches that pond. Mixing of these two tools are the best option you have. And so far it's not that bad, because like, what is that? H2SO4 getting love with CaO gives you CaSO4 plus water. Not that bad. But issue is costly, meaning this small stream, it's expensive, because the lime is not itself that expensive, but shipping hundreds and thousands of tons of it, yeah, it becomes very expensive very quickly. It might as well become a scenario where same way coal mine could have a freight locomotives that are moving it, like a freight train moving bulk load. You could literally have a freight train bringing lime there, and that would be expensive. So that's there. And because here's the deal, if you are not taking care of it, regular maintenance, it's useless. So many plants, I have linked some amazing work in Pennsylvania, if I'm not mistaken. They have done some amazing work. I've linked, and they have made good videos showing how the heck it works. I would urge you to watch it. And in that, they are very clear about it. It's like it has to be constantly maintained and monitored. If you do not, it becomes ineffective. So because of the cost, because of the fact that it requires periodic maintenance, it's not something you put it and forget it. That's the worst aspect of it. If we had something that is like put and forget, we will have solved this problem, but we do not have such technologies. It requires constant maintenance. And be mindful, this is after the mine has shut down. When mine is running with this sort of tools, it's like minor inconvenience. Not awesome, but manageable. And we have learned the hard way that we need water more than we need the minerals. So people have learned it. Like even the miners would be like, yeah, I get it. Like mine owners, they're like, yeah, let's not poison the water that I drink. So we have understood. It's just that when it shut down, then what the hell you do? So this sort of scenario is an issue. So we have mitigation strategies. Primary strategy is using CaO and O2 to take care of situation. That's the best tool on large scale that we have. Does it remove 100% of the problem? No. But does it make it low enough where nature can take care of it? Yes. Be mindful, nature can solve almost all problem as long as low enough. Meaning nature can literally create a microbial life structure that can survive in Chernobyl reactor building. It can do that. It's just low enough. Basically, you have to give it time. Cool down, bro. Chill, bro. It can handle it. So what can we expect in the future? Well, reality is we are realizing this. South Africa is learning this now. That's what happened actually. West realized all their industrial might is awesome and all that, but if it poisons their own land, their own soil, their own rivers, it's not worth anything. Be it America, be it Europe, both of them like, yeah, we don't want this here. Now, they did try to sort it out. They did build technology to it, but cost started to go up. But in the era of globalization, especially multinational corporation, they're like, what if we outsourced it? What if we did not give a damn about it? What if we give South Africa money and they're like, let's poof our future and get the coal from there, or minerals, or some heavy minerals, or China did that. So we learned this the hard way, that economic penalty is not a way. We have to find a use for it where it becomes effective thing. That's the critical aspect. Law is not the answer. We have learned this hard way. Like law is just not going to work. You have to force someone to do something. It's not going to work. You have to give them advantage of doing so. That's like what is the essence of last 150 years? That's the essence. You cannot force it. You have to make it viable. So how do we make it viable? Well, some approaches have been taken. For example, the pond where I'm saying you are doing the settlement, it has a lot of stuff, rust and stuff. So somebody figured out, hey, this pond that we have this stuff, these are what we call residuals. So there is a benefit of this puppy. This puppy will eat up phosphorus like there is no tomorrow. Like, is there a benefit of that? Is there a use of it? Thankfully, yes. In basically municipality water treatment plants and agricultural water runoff treatment plants, basically water treatment plants, they've realized that we have way too much phosphorus going into those streams because of our improper farming practices. If we do not remove it, it triggers the same issue. But here's the deal. Now we are using two poison to cancel each other out. Poison number one, poison number two, they cancel each other out. They make love with each other, they chill out. So that's one way of using it. And because of the amount and the constant supply requirement, it's a good use. It's a good financial stream. It will reduce the burden on the municipality or the government that is taking care of this thing. Little bit helps. Then you have the gold mine that is happening right now. The amount of R&D that is poured into this, it's bonkers. It's recovery of rare earth element. I randomly noticed 5 years ago, like way too many papers started to come out on this. And like I'm checking right now, and then I'm saying everything is in 5 years ago. It's like, what happened? China increased the price. And I'm like, I see. That will amplify it. Now, why do you have rare earth mineral here? Here's the we kind of mistake this. Is like when we say iron mine, we expect there to be iron there. Here's the deal. Anywhere you are standing, if there is a soil below, there is iron below. And why don't we mine everywhere? Is the concentration. All the game, basically all the mining industry is concentration. You will find diamond, you will find ruby, you will find platinum, you will find everything under the sun, literally under your foot. The issue is the ppms, basically how much is there. Now, water has this ability to dissolve everything. Acidic water has the ability to dissolve everything. So what does that mean? That simply means somebody thought of it, and actually in late 50s, 1950s, somebody figured out, like, let's just study what the heck is in the water. There was rare earth minerals there. Nobody bothered with it because that time there was not that much use of it. They were just like, oh, we had water that is intake into the treatment plant that had this much metals, and output had almost no metal. So they were very happy with it, and they did the calculation. It's like what percentage of stuff is there, what metal concentrates are there. They did not knew they were literally standing on a gold mine. All these things have is what we call rare earth minerals. So is rare earth mineral available in everywhere? Short answer, absolutely. If there is a earth crust, it's there. It's just the ppms of it is too low. What is the best way of getting ppms out of it? Water. What are you dealing with here? Water. So somebody figured out, like, and the concentrate output is higher than the best mines there are. Not every location, let that be very clear, but it's more than enough to justify mining that puppy. Meaning you have a mine, okay, mine is running, you are gonna spend money on this, but what if that residual that you are dealing with, you also mine heavy, basically unique metals out of it, rare earth materials out of it. At that point, it can reduce the cost of this operation to such a point where it's like minor inconvenience, economically speaking, or to profitability. Because be mindful, once you have a source of actually extracting basically heavy metals out of it, you also price lock it. Meaning you have so much supply that if China is like, I'm going to increase too much price, like, man, we have the solutions. It's like, why do we pay you more and then ship it? Might as well increase this plant. So it has a very good feedback loop. You always want feedback loop. You never want single point of failure. So recovery of rare earth minerals, and everybody is seriously looking into it now. And the results are early results. Let me be very clear. This is very early on. Is the core is there, the material is there, the concentration is there, and it also has some advantage that it's already in liquid state. We do not have to do we don't have to do that. It's there. It's in liquid form. It's dissolved. All they have to do is figure out a way to basically run some catalyst, run some equations and some balancing things. So it does not have too much consumables, and output is money. So this sort of ponds where they take care of the residuals and they remove the water from it and all that, everything is fine, everything is great. It's just like, if they can get like $100,000 out of each bag, will it eliminate all the cost? Hell no. Right now, no. But it will keep running the plant would be like, well, minor inconvenience. So there is some genuine technology, some genuine financial incentive to do this. And then we have to come to the nature side, is that using microbe to reduce the cost. How that can be done? Yes, nature can sort out a lot of things. There is ecology that can survive in literal, basically bottom of the sea while next to a volcano. We got it. Nature is like, bro, I got this. Nature can survive radiation environment. Nature is like, bro, I got this. What we have to do is just tame it enough. What does taming it means? Basically, you take the AMD and you throttle it even a little bit. Nature can put a foothold. The moment nature puts a foothold, it can break it down. It's like, bro, I got this. All we have to do is basically chill it a little bit. Instead of trying to solve all the issue ourselves, we all have to do, hey, let's tame it a bit. Of course, consume lime on it. Tame it a bit, aerate it a bit. Let's say pH level is 2. Let's bring it to, let's say, 4.5. At that point, microbial lives that are acidic in nature, they're like, I got you, fam. That's a long-term solution. So these elements, these three elements, basically figuring out what can we do with the residual, figuring out how to extract money out of the stuff, and using biology so it's long-term stable. These are the way we can have mining industry in the future without causing instantaneous annihilation of all living things on Earth. So the future has some potential here. So this was my presentation on AMD. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.